Welcome to our exploration of East Africa's geography. Look at the Mabira forest. It is a dense, thick blanket of broad-leafed trees and endless green. Now, compare that to the Karamoja region. The landscape is dry, dusty, and the plants are sparse and tough. Both of these locations are in Uganda, right near the equator. So why do their ecosystems look completely different? It comes down to the difference between weather and climate. Weather is what is happening outside right now, like a single rainy afternoon. Climate is the long-term pattern, the average weather conditions recorded over 30 years or more. Those invisible, long-term geographic forces act as architects of the landscape. They dictate exactly which plants have enough water to survive in each specific region. To see these forces at work, let's start at the Lake Victoria Basin. Massive water bodies act as powerful climate engines. This diagram shows how convectional rainfall works. The intense equatorial sun beats down on the lake, evaporating water. That vapor rises, cools, and condenses into clouds, pouring back down as heavy, reliable rain. Because this cycle happens all year round, it creates an equatorial climate with double maxima rainfall, meaning two main wet seasons. This constant moisture is what feeds dense tropical rainforests. Naturally, people migrate toward this reliable water. The lake basin is the most densely populated part of East Africa because farmers can grow cash crops, like harvesting coffee and matoke, all year long. But if you travel straight west along the equator to the Rwenzori Mountains, you hit freezing temperatures and snow. This chart illustrates the effect of altitude. The higher you climb above sea level, the colder the air gets. We call this altitude mulzonation. The dropping temperature forces the plant life to adapt at every level. You start with warm tropical rainforests at the base, transition through bamboo, and end up with tough, cold-resistant alpine shrubs near the icy peaks. A giant lake can create a year-round rain engine, and a tall mountain can create snow on the equator. These local geographic features overpower the baseline heat of the region. Now let's move away from the mountains and lakes and head northeast into the dry plains of Karamoja. This diagram shows how relief, or mountain ranges, affect rainfall. As moisture-heavy winds hit a mountain, they are forced up, dropping their rain on the windward side. By the time the air crosses over the peak, it is entirely dry. That dry side is called a rain shadow. Because Karamoja sits in one of these rain shadows, it experiences a semi-arid climate with very low, unpredictable rainfall. The lack of water dictates how communities live. Because farmers cannot rely on rain for crops, people live as nomadic pastoralists, moving their cattle and donkeys across the dusty landscape to chase scarce water and pasture. Let's test this concept with some raw data. This table shows Station A with 1,800 millimeters of annual rain and an average temperature of 25 degrees Celsius. Station B has only 400 millimeters of rain and 30 degrees. Which station supports a lush forest and which a scrubland? Station A gets plenty of rain and moderate heat, making it perfect for a tropical rainforest and large-scale timber production. Station B is hot and dry, supporting only arid scrub. By checking just temperature and rainfall, we can accurately predict both the natural ecosystem and how humans will survive in it. We usually assume plants only grow because it rains, but massive forests actually help generate that rainfall. The engine behind this is evapotranspiration. Deep roots pull groundwater into the tree, releasing it into the atmosphere as water vapor. But human activity threatens this system. We are rapidly clearing natural savannas for single-crop agriculture and cutting down ancient forests to meet a massive urban demand for charcoal. When we remove the tree cover, the evapotranspiration cycle breaks. The air becomes drier, the rain stops falling, and we trigger desertification, where once fertile soil turns completely barren. Expanding cities further disrupt local weather. We replace natural greenery with massive stretches of concrete, tarmac, and dense buildings. These materials absorb the sun's energy, turning urban centers into localized heat islands. The city becomes measurably warmer than the countryside right next door. Protecting East African vegetation is about securing the exact water supply millions of people rely on to survive. To learn more about how our geography shapes our future, check out the resources on the Yaka Digital Network.